In this video, we will discuss the problem bipartite graph. Previously, this problem has been asked in Microsoft and Flipkart. The problem says that we'll be given a graph and it will be represented using an adjacency list. So what we have to do is we have to check whether that given graph is bipartite or not. So what does it mean when we say a graph is bipartite or not? So suppose this particular graph, suppose a graph has been given to us, okay? So we have to say whether it is a bipartite graph or not. So basically what happens is we have two colors, right? We will have two different colors, okay? We will have two different colors, and what we need to do is we need to assign, like for every node we need to give a color, right? For every node, right, for every node in the graph we need to color it, and we need to color it in such a way such that no two adjacent nodes have the same color. No two adjacent nodes have same color. If this condition is matched, then it will be bipartite. Otherwise it will not be bipartite. So basically what happens, two different colors are there and you have to color the whole graph using these two different colors. For every node you have to color it, and you have to color it in such a way such that no two adjacent nodes have the same color. So let us say that if we have two colors, let's say I have a color yellow and I have a, let's say, a color green. Okay, these two colors are available for me. So maybe what I can do is I can color this node as yellow. Then what will happen, this node I can color as green and this node I color as green. So in this way you can see that this graph is bipartite. Okay, why this is bipartite? Because basically because no two adjacent nodes are having the same color. If you see this and this, so these two are adjacent and they are not having the same color. And if you see this and this, these two nodes are adjacent and they are not having the same color, right? So that's the case here. Like suppose in place of this, if I do it like this, so this is not valid, okay? But basically this graph is bipartite because I can color it like this. So basically if you see, suppose that this was your parent, and like these were the children, right? These were the children. So you can see that if the parent color is there, so parents children will always be adjacent. So that means whatever the parent is, its children will have a different color compared to the parent. Okay, that's one thing that you can easily see. And now let us take another example. So let us suppose that we have been given a graph like this. Suppose we have been given a graph like this, which is having four nodes. So in this case, what we can easily try to observe is, if we observe for this graph, so basically let's say we have two colors again. So if we start from this, so let's say we color this as yellow. So according to this node and this node is my adjacent, so I have to color it differently. So I'll color this as green and I'll color this as green, because suppose that this is my yellow is my starting point. So both these nodes are my children, right? This and this node is my children. So I need, since my children will be adjacent to me, so I need to color them differently. Then what will happen with respect to this, you can observe that this is the child, right? And here you can try to color it as yellow because a different color is required. And now you can easily see that this graph has become bipartite. Why? Because these two are not having the same color, these two are different color, these two are having different color, these two nodes are having different color, these two nodes, adjacent nodes, are having different color. So that's why it's a bipartite graph. Okay, now let us try and take one more example. Suppose in place of this, what I do is I have five nodes. Like if I have five nodes, then what will happen? So suppose this kind of a situation is there. So what will happen? Suppose I start with yellow. Okay, then what will happen with respect to this and this will be colored as green. Then what will happen, since this is green, so this will be yellow. Okay, and since this is green, so its child will be what? Its child will be yellow, right? So you will do this. In that case it is not bipartite. Now you will say that instead of this, what you can do is, if this is yellow, right, if this guy is yellow, so you can color this guy as green. But even if you do that, so you can see that again this and this are the same, so it's not bipartite. So like you can easily observe that in such situations the graph is not going to be bipartite. So now the thing is that how to implement this functionality here. So basically what we can observe is that like we will start with the parent, right? Our parent, like we will start with the starting node. Let's say we will start a DFS from 0. Okay, so let us try and name this. Okay, first of all let us try and name this graph. So let's say this is the node with the value 0, like this is the node 0. Okay, this is the node, let's say this is the node 1. Like basically there are nodes, right? So basically what will happen, like if you will start from a particular node, right? So since the nodes are numbered from 0 to n-1, so you'll start from the node 0, you will start your DFS from there, and initially you will say that every node is having no color, right? So initially you will say that like you have a visited array. So instead of a visited array, you will say that you will have a color array. Okay, and in like the colors, possible colors are 0 and 1, right? Either the color will be 0 or the color will be 1. Basically it will indicate yellow and it will indicate something like green. Okay, so basically the 0 and 1 are indicating two different colors. And if a graph, if a particular node is not colored, so it will be indicated by -1. Okay, indicating that it is not colored. So basically if it is not colored, then I'll color it with a color that is different than its parent. And then when I color it with a color that is different than its parent, then I'll call the DFS for its children and I'll color it. Let's suppose that I'm currently at a particular node, right? Suppose that I'm currently at a particular node and I color it with the color 1. So all the children of that particular node will be colored with the color 0, right? That is what I'm expecting. So this is what I'll be doing. And suppose that what happens, I call the DFS call. Okay, suppose what happens if I call the DFS call, and if its child is already, if it's like, let's say I start from here. Okay, so let's take a smaller graph for the stimulation. Let us say that I've been given this graph. Okay, suppose that this is the graph that has been given to me. Let me write it like this. Okay, suppose this is the particular graph that has been given to me. So in this graph, what we can easily try to observe is, so basically what happens, let's say I color it with green. Okay, if I start the DFS from this and I color with this green, so what will happen, I'll call for my child. Okay, I'll call for my child, and what will happen, let's say I call for this child and then I color it with yellow. Okay, so that will be fine. Then what will happen, like let's say I name the nodes first of all. So let's say this is node number 0, this is node number 1, this is node number 2. Okay, then what will happen, if this I color as, let's say 0, or let's say I color it with green color, then what will happen, this is the child, right? 1 is the child. So suppose I started the DFS from 0, right? So in DFS of 0, so what I will do is I'll color this with green, and then I'll call for my children. So I'll call the DFS for 1, for the very first child I'll call for. Then I'll color the child that is with the different color than me. Then this will be colored like this. And then what will happen? I'll call the DFS for my another child. So I'll call the DFS for 2 as well, and I'll color it because it is not colored. It is currently -1. So I'll color 2 as well. So 2 will also be colored as yellow because 0 is the parent. 0 is the parent of 1 and 0 is the parent of 2 as well. So since 0 is the parent of 2 as well, so 2 will be colored as yellow. Now, like you will say that okay, that's like you will say like what will happen, like let's suppose that this part is there, right? Basically what will happen, or maybe you can suppose it like this. Suppose you are currently DFS for 0 you called, and then you call for DFS of 1. So it will color it like this. Then like you will iterate through the adjacency list of all the like 1. Okay, so in 1 you will call the DFS for 2. Okay, when the moment you call the DFS for 2, so what will happen, it will be colored with a different color than 1. So it will be colored as green. And after that what happens, after that you move up, right? You move up, and then what happens, like in the adjacency list of 1, 2 was present, so you colored 2 with the color green. But now you need to check this. Now you need to see that in the adjacency list of 0 as well, in the adjacency list of 0, 1 and 2 both were present, right? When you call the DFS for 1, so in 1 you call 2, you have already called 2, but now you can see that 2 is already colored, right? When you are at 2, when you come back to 0 after calling the DFS for 1, okay, when you come back from here, so this call has been made, then you call for 2. When you call for your child, when 0 call for its child, and it can see that it is already colored, right? The color is not equal to -1. So I can easily try and observe that since the color is not equal to -1, so the color is already there, right? So I can see that the color is what? The color is, if the color is different than me, if this is suppose the parent, right? And this is the child. So if my child's color is different than me, if it is already colored due to some other DFS call, so if it is having a different color than me, then there is no problem. The graph is like the graph is perfect. The two nodes, since the two nodes are not having adjacent nodes are not having the same color, so that condition is fine. But if they have the same color, then in that case immediately I'll return a false. Okay, that is what I am going to do. Now let us try and write the code for this particular approach. So what I will be doing is, I'll be having a vector int let's say color, and like let's limit its color and v number of vertices. So I'll initialize all the colors initially as -1. Okay, and then what I will do is I'll say that int I starts from 0. Okay, and I is lesser than v, and then I'll do an I plus plus, right? And what I will be doing here is I'll say that if the color of the ith node is equal to -1, if the ith node has not been colored. So if the ith node has not been colored, then I'll try to color it, right? Now why did I directly not call the DFS for the node, and I called the DFS like in a loop? Because what will happen, like there can be several connected components, right? Suppose what can happen is, suppose that this can be one of the graphs, right? Suppose like this can be node 0, 1, then 2, and then 3. Okay, then another situation could be like this, right? Suppose like this will be the node number 5, like 4 and 6. Basically you can see that basically if total 7 nodes were there, so they can be two or more different components as well. So if you will check, if you will call the DFS for, if you will call the DFS for 0, okay, then you will say that okay, this graph was bipartite, and that's perfectly fine. But actually this is not bipartite, right? So in that situation you should return a false basically, right? So that's why you will be checking for every ith node that's not color, that is for different components you will be checking. So what I'll say is that int answer that I'll be getting from the DFS call, so the DFS will be boolean in nature. It will return immediately a false if the graph is not bipartite. So I'll start from the ith guy, I'll pass the adjacency list, okay, and then I'll pass the color array, and I'll initially pass the color at 0, right? So basically, as I mentioned, I'll be having two different colors, right? I'll always be using, like for coloring, I'll be using the color 0 and the color 1 because I can use numbers. So it will be easier for me to switch, okay? So suppose that what happens, suppose that the parent color, okay? Suppose that the parent color is 0, okay? So the child color, like parent color is 0, okay? So if I have called for the ith child, okay, so if I have called for the ith child, like for the child, so color of the child will be what? Color of the child will be nothing but 1 minus parent color always. Why? Because if my parent color is 0, then what will happen? The color of the child, if my parent color is 0, right? So in that case, color of the child will be 1 minus 0, that is nothing but 1. 1 minus parent color, that is nothing but 0. So 1 minus 0 will give me 1. Otherwise, suppose my parent color is 1. So in that case, what will happen? The color of the ith guy will be 1 minus parent color. Okay. So if the parent color is 1, so 1 minus parent color, 1 minus 1 will be 0. So that's how the relationship will be different, because you can see here if the parent color was 0, so the child color is 1. Okay. And if the parent color was 1, so the child color is 0, right? So that's how I'm going to fluctuate by using this concept. Or otherwise you can use a XOR as well. You can do one XOR parent color as well. So that will also work, because the XOR concept can also work here. Okay. So this is one thing that we'll be doing. And what I will say is that if this DFS call returns me a false, right? If this DFS call returns me a false, then I will say that this graph is not bipartite, and I'll return a false. So moment any DFS call returns me a false, so I'll return a false. Otherwise, after performing one or more DFS calls, depends on the number of components. If I never return a false, so in the end I'll return a true, indicating that the graph is bipartite. So let us now try and implement a DFS function. So I'll say that bool DFS function is going to be there, in which I'll have the int I, okay, I'll have the vector int adjacency list, okay, I'll have the adjacency list, and what I will, like, I'll have the adjacency list. Apart from this, I'll also have the color array. So vector of vector int ampersand color is what I'll be having, okay. And what I will be doing is I'll have the int parent color, okay. So basically I'll have the parent color with me, as I've passed. Initially I'm passing the parent color as 0, okay. So what I'll say is that the color of the ith child, okay, the color of the current child, color of the current child will be nothing but 1 minus parent color, as I have already discussed. And then what I will do is I'll say that I'll iterate for all the children, okay. So I'll say that auto my child is to adjacency of I. So basically this means that I'll iterate through the adjacency list of the ith node, and I'll run for it all of its children. So if it happens that the color of the ith child is equal to -1, so that means it is not yet colored, right? If the ith child is not colored, so that means that I'll call a DFS call for it, okay. So I'll call the DFS call for my child, and what I'll pass is I'll pass the adjacency list, I'll pass its color, right? I'll pass the color array, I'll pass the color array, and I'll pass the current color of the ith node. This is what I'll pass. And since this DFS function is boolean nature, so it will return me a temporary answer, right? Let's say it will return me a result, okay. So if this DFS call, like after I've called for my child, so if this DFS call, right, if this result is equal to false, if this DFS call returns me a false, okay, in that case I'll do what? I'll say that the graph is not bipartite, I'll simply return a false, okay. This is something that I'll be doing. And after this part is done, so suppose that else what happens, else if it happens that suppose my ith child, like if my child like I'll say that not color of I, basically color of the child, okay, sorry. So basically I'll write if the child is color equal to -1. So if it has not been colored, then I'll call the DFS for it. I'll check if the DFS returns a false. then I'll return a false. Otherwise, else what happens, if the child has been colored, right? If the child is covered, if the child is already colored, so if it's not -1, so if the child is colored, so I'll check if the color of my child is equal to my color, right? If the color for the child is equal to the color of the parent, right? So in that case also I'll return a false, right? Because as I mentioned, if the child's color is same as the parent colors, so in that case I have to return a false, because the graph will no longer be bipartite. And once I'm done with this particular graph, once I'm done with the DFS part, so if I never return a false from this part, so I'll say that I'll return true for this part, indicating that this much part is perfectly fine and the graph seems to be bipartite. Okay, so that is why I'll return a true. Let us now try and compile this code to see if it works on the samples. Okay, so we are having some compilation error, so it is saying that vector of this thing, right? So I need to use a vector like this, and let's see another error. So color. Okay, so let's try and compile this to see if there is any other error. We might have some more error. Yeah, so it's getting this as same expected output. Let us try and submit this code as well. Okay, so you can see that our code was able to pass all the test cases. And now talking about the time complexity of this code. Okay, so the time complexity will be nothing but the time complexity of the DFS. So time complexity will be order of v plus e, and the space complexity will be order of v, because for all the v nodes, all the v different nodes that are there, we are using the color array, right? So that's why it will be there. And like you can also implement this question using using the BFS approach as well, and the DFS approach will also work. So both of the approaches are perfectly fine. In case if you understood the explanation, so make sure to hit the like button. Thank you for watching this video.